Welcome to the Deep Dive, where we unpack fascinating ideas and, well, make them crystal clear for you. Today, I want you to truly imagine something that feels like it belongs straight out of a sci-fi movie. Imagine making an object float in thin air, using only sound. No strings, no magnets, just sound waves. It sounds like magic, doesn't it? We're about to take a deep dive into acoustic levitation.
And you're absolutely right. It feels like magic, but it's pure cutting-edge science. Acoustic levitation is a real technique. It uses incredibly intense sound waves to suspend materials without any physical contact at all. Think of it like an invisible hand, maybe, one made entirely of sound-defying gravity in ways we're only just beginning to really explore.
Okay, so when we talk about making things float with sound, what's the fundamental principle here? Is it just sheer force, or is there something more subtle going on with these sound waves? And, what kind of sound are we even talking about? Is it loud?
It's both subtle and, well, incredibly powerful. We are talking about high-intensity sound waves, yes. Usually it's ultrasound, so it's
Yeah.
inaudible to us, around 150 to 160 decibels. Now, that's incredibly loud, objectively, but because it's ultrasound frequencies far beyond our hearing range, we can generate that force without, you know, deafening anyone.
Ah, okay. So the frequency is key.
Exactly. And these very short wavelengths are perfect for manipulating tiny objects. The core idea is generating enough acoustic pressure upwards to counteract an object's weight. And what's truly revolutionary here, compared to, say, magnetic levitation.
Which only works on certain things, right?
Right, very specific materials.
Yeah.
But acoustic levitation, it can work on almost any solid or liquid you can think of.
That's fascinating. So it's not just volume, but the type of sound.
How do these waves actually hold something up, though? Do they just kind of blast the object upwards?
Not quite like blasting it, no. It typically relies on creating something called standing waves.
Hmm.
Imagine a sound emitter, like a tiny speaker, sending waves towards a reflector surface.
These waves bounce back, and they interfere with the incoming waves. They collide, in a way. This interference sets up a fixed pattern in the air. You get areas of really high pressure and, crucially, areas of very low pressure.
Like ripples meeting on a pond, but in the air?
Sort of, yeah. And think of it like two waves on a string, creating those still spots where they cancel each other out, those still low pressure points. They're called nodes,
Nodes, got it.
and that's where the objects get trapped and suspended. The upward force from the sound in that specific spot perfectly balances their weight, holds them motionless. Now, this works best for small objects, usually a few millimeters across or weighing just milligrams. Their size needs to be comparable to or smaller than the sound's wavelength.
It sounds incredibly cutting edge, but what's really interesting is how long these basic ideas have actually been around. It feels like we're just now unlocking their potential. Can you take us back a bit? Where did this all start?
Absolutely. And it goes back further than you might think. The first seeds of this idea were sown over a century and a half ago. Back in 1866, a physicist named August Kunt. He was actually trying to measure the speed of sound in gases inside tubes.
Okay, so not even trying to levitate things.
Not at all. But he noticed something profound. He saw dust particles inside the tubes accumulating in specific patterns, pushed around by the sound waves.
Yeah.
He realized sound could physically manipulate matter. That observation was, well, foundational, even if actual levitation was still decades away.
Wow. So from seeing dust move in 1866, it took nearly 70 years for someone to actually make something float. What was that first breakthrough like?
Indeed, a big gap, but the technical challenges were significant. The first true acoustic levitation was achieved in 1933. Two researchers, Carl Bix and Hans Miller, they successfully suspended small liquid drops using ultrasound. That was a huge step. And much later, just for fun apparently, someone named Hilary St. Clair managed to levitate a small coin in the 1960s.
A coin. That's amazing. Okay, so fast forward a bit, the 1980s. NASA gets involved. Why would a space agency be interested in floating things with sound?
Yeah, NASA's interest was mainly about studying liquids in microgravity.
Mm.
You see, on Earth, gravity in containers affect how liquids behave. In 1985, a team led by Taylor Wang actually took an acoustic levitator aboard the Space Shuttle Challenger.
On the shuttle. Wow.
Yeah, levitation allowed them to hold and study liquid drops without any container walls. No contamination, no distortion from surface tension effects dominating in zero-G. It was critical for certain experiments. A massive leap, really, from a lab curiosity to space-tested tech.
Okay, so what about more recently? How has our control over these sound waves evolved since the 80s?
Well, a really significant modern step has been the development of what are called phased arrays of ultrasonic transducers. PATEs, for short.
Phased arrays, like radar.
Similar principle, yes. Instead of just one sound source and one reflector, imagine a grid of tiny, individually controlled speakers.
Each one can emit ultrasound precisely timed. It's like conducting an orchestra of sound emitters. You can sculpt really complex sound fields in 3 dimensions, dynamically. This allows for much more precise manipulation, moving objects around, and you don't even necessarily need a fixed reflector anymore.
So much more control.
Exactly. And a huge boost for accessibility came in 2017 with an open source project called TinyLev. It made building a basic acoustic levitator much cheaper and easier, opening the door for more researchers, students, even hobbyists. It really helped democratize the field.
That's brilliant. Now, let's talk about some of the really mind-blowing examples we see today. I think many of us have seen those viral videos, particles appearing to almost teleport or dance around in midair, controlled by sound. But what else? I heard something astonishing, that scientists have even managed to levitate living creatures.
They have. It sounds incredible, but yes. Scientists have successfully levitated small living things like tiny insects, ants for example, and crucially without harming them. It shows an amazing level of gentle, precise control is possible. And pushing the boundaries even further. Back in 2018, researchers at the University of Bristol demonstrated something they called acoustic tractor beams.
Tractor beams? Seriously? Like in Star Trek?
Well, maybe not pulling spaceships yet, but they successfully trapped objects significantly larger than the sound wavelength. They levitated a polystyrene sphere about 2 centimeters wide. That was a big deal because previously it was thought you were limited to objects smaller than the wavelength. It definitely hints at those sci-fi possibilities, pushing what we thought sound alone could do.
Okay, so beyond the cool demos and floating insects, what about practical applications?
Yeah.
Is this technology actually being used now?
Oh, yes, definitely. In electronics manufacturing, for instance, it's
Yeah.
being used for precise, contactless handling of delicate components. Think tiny microchips or sensitive sensors. Levitation avoids physical contact, preventing damage or contamination during assembly. That can significantly improve quality and reduce waste.
Right, for things too small or fragile for robotic arms. Makes sense. Any other industries?
A huge one is the pharmaceutical industry. They're using it for something called container-free processing, especially for drug crystallization.
Container-free, how does that help?
Well, when you crystallize a drug in a container, the surface of the container can introduce impurities or influence the crystal structure. By levitating a droplet of the drug solution and letting it crystallize while suspended in air, you can potentially get much purer, more uniform, and potentially more effective medications. Places like Argonne National Lab are doing significant research in this area. It could fundamentally change how some drugs are developed and made.
That's incredible. Looking further ahead then, the possibilities seem vast. You can imagine handling hazardous materials, maybe radioactive or extremely hot substances, without any physical contact. Or maybe even assembly lines where tiny components just float into place. Contactless assembly. It feels revolutionary for manufacturing.
Absolutely. And perhaps a more accessible future use. Think about education. Imagine interactive museum exhibits where kids can manipulate floating objects just using sound controls, or educational toys that demonstrate physics principles in this really tangible, almost magical way. It can make science incredibly engaging and really inspire curiosity, making the invisible visible, in a sense.
Oh, what an incredible journey we've taken it in. Seriously. From an almost accidental observation back in the 1800s to this versatile tool with just immense potential. We've seen how sound, something we usually just think of as hearing, this invisible phenomenon, actually has the power to manipulate the physical world in these truly surprising ways. It's clearly not just what we hear anymore, but what we can do with it.
Exactly. And that's maybe the final thought to leave people with. It's a powerful reminder, isn't it, that scientific reality, what's actually possible, can often reach and sometimes even surpass those fantastical visions we see in science fiction. Just imagine the practical, maybe even wondrous ways this invisible, silent force might soon shape our daily lives, from medicine to manufacturing to maybe even just play. It's fascinating to think about.